Now in this video, we're going to start talking about different types of polygons. Okay, so we're going to first start talking about quadrilaterals, which are four-sided figures. Okay, and see what we can say about those. Okay, now so for quadrilaterals, we can always come to our polygon tool here. We want a quadrilateral four-sided. We click to get started. Each click is a vertex. There's 2, there's 3, there's 4. We're finished. Double click. There's our quadrilateral. Okay, we can name it obviously with the consecutive letters. It's nice. Okay, now we want to talk about drawing the diagonals. Okay, so from any one vertex, we can come here and we can click the segment and we can draw the diagonals. Okay, now from one vertex, as you can see, all I can draw is, all I can draw is one diagonal. Okay, now now the diagonal has separated that quadrilateral into 2 triangles. Okay, and of course we know that each triangle has 180 degrees. Okay, so we got 180 degrees represented in each triangle. There, 180. Okay, we got another 180 degrees represented. Okay, 180 degrees over there. Okay, in the other triangle, so we'll put that into place, right? And that will tell us that we've got 2 triangles in our figure. Okay, 2 triangles in our figure, each with 180 degrees. So it's telling us that the total interior angle in this quadrilateral would be 2 times 180, which would be, of course, equal to 360 degrees for the total angle measure of a quadrilateral. Now, if it's a regular, that means all sides or all angles are equal, then each one's going to be 90 degrees. Okay, all right. Let's go on and look at the 5-sided figure. Okay, and a 5-sided figure, okay, 5 sides, is known as the pentagon. Okay, the pentagon. And to draw the pentagon, again, I can go right to my polygon tool, click on the polygon tool, 1, 2, 3, 4, 5, double click. Okay, name the vertices. Okay, and move on from there. Okay, now out of A, I can draw a diagonal here, and I can draw another diagonal over here. Okay, now as you can see, the number of diagonals that I've drawn is 3. Okay, but I want you to think about the diagonals in terms of, how they relate to the number of sides. So the number of diagonals here with a 5-sided figure was 5 minus 2, which is equal to 3. Okay, so I get, 5 minus 3, 5 minus 3, which is equal to 2. Okay, now how many triangles are formed? Well, I've got 1, 2, 3 triangles formed. Okay, so the number of triangles formed, is 3, but that is 2 less than the number of sides. So that's 5 minus 2, which is equal to 3. Okay, and the reason why I've done this will become clearer in a moment. Okay, we have 3 triangles, each with 180 degrees, so we can tell that the angle measure of all the angles here, and you can come back and you can actually prove this if you like, but the angle measure, is going to be 3 times 180, 3 times 180 degrees, because we got 3 triangles, which of course is 540 degrees, 540. Okay, so that's our total angle measure. All right, let's go and build a 6-sided figure. 6-sided figure known as the hexagon. Okay, 6 sides is of course the hexagon. And with the hexagon, okay, again, we can draw the polygon. We go 1, 2, 3, 4, 5, 6. Double click. There's our hexagon. Okay, from each of the vertices, if you want. Okay, we can. We got 6 sides. So if I want to draw the diagonals, then I say, okay, out of A, I can go to C. That's 1. Out of A, I can go to D. That's 2. Out of A, I can go to E. So that is 3 diagonals. Okay, so the number of diagonals that I can draw here is 3, but that seems to be the number of sides minus 3, which is equal to 3. Okay, so what we're doing is trying to establish a pattern here for how we determine what these number of diagonals are going to be. Okay, number of triangles: 1, 2, 3, 4 triangles. 4 triangles, 6 sides. So I guess we're going to say 6 minus 2. Okay, 6 minus 2, which is of course is equal to 4. Okay, and the total angle measure. Well, we have again we have each of these triangles, okay, at 180 degrees. Okay, and we have 1, 2, 3, 4 triangles. So we're going to say that the total angle here is, okay, 4 times, okay, 4 times the 180 degrees, which is going to equal, okay, 720 degrees, right? 720 degrees is the total angle measure for the hexagon, okay? Total angle measure for a hexagon. Let's go and build a I don't know. Let's just build however many sides we want. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8. Stop there. Okay, 8 hexagon. All right. Let me change this around a little bit. Okay, and make it look a little bit more hexagonal, if you will. Okay. All right. So here's my hexagon, my octagon. Right. Got 8 sides. Okay. All right. 8 sides, 8 angles. A, B, C, D, E. I've got 1, 2, 3, 4, 5, 6, 7, 8. So I've got an 8-sided polygon. So I'm just going to refer to that as 8 sides. Okay. So that's what we call the octagon, right? Okay. So 8-sided polygon is the octagon. All right. And let's go back to that. Okay. Sorry about that. So this is called our octagon. And it's 8 sides, of course. And what we're trying to do is a number of diagonals from one vertex. Here we go. Draw the diagonals from A. There's A to G, A to F.
Jake Ballard, please come to the cafeteria.
A to E, and A to D, and A to C. Okay? So, we have the number of diagonals drawn is 1, 2, 3, 4, 5. Okay, so we have 5, but in essence, we started out with 8. We subtracted from that 3, which gives us equal to 5 total diagonals. Okay, so we have 5 total diagonals. 1, number of triangles, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we have 6 triangles in here. Okay, so let's account for that. That is 8 minus 2, which is equal to 6. Okay, and we have 6 triangles, each at 180 degrees. So what's our total angle measure? Well, it should be 6 times 180. Okay, 6 times 180. So let's put that in. Okay, as 6 times, okay, 180. All right, 6 times 180. Of course, that would be 3. What would that be? 6 180 would be well, 48 1080, right? 1080. Okay, would be the total angle measure. 6 180 is 360, 720, and another 360. So we've got 1080 is the total angle measure. Now let's kind of generalize this, okay? Go back, okay, quadrilateral, 4 sides, okay, 1 diagonal from each vertex, separating it into 2 triangles, each with 180 degrees for 360 degrees total. Pentagon, okay, was 5 sides, okay. The number of diagonals drawn from each vertex was 2, which was 3 less than the number of sides. The number of triangles formed was 2 less than the number of sides, so that's 5 minus 2, or 3. And the total interior was the total number of triangles, 3 times 180 for 540. Okay? Then we look at the hexagon, the 6 sides. Okay? Drawing the diagonals from one vertex, we have 6 minus 3, or 3 diagonals from each vertex, separating it into 4 triangles, or 2 less than the number of sides. Each triangle with a angle measure of 180. 4 times 180 gives us 720. And then we said for the octagon, okay, 8 sides, okay, 8 sides, 5 diagonals from each vertex, 3 less than the number of sides. Triangles, 2 less than the number of sides. Total interior angle, the number of triangles times 180 each, okay? So we're going to generalize this for what we call a n-sided polygon. That is however many sides you want, n sides. So it's basically an n-sided polygon is called an n-gon, okay? For 12, it's a 12-gon, but we know it to be a dodecagon, okay? The number of diagonals that we have, okay, coming out of each vertex, going back, okay, I believe that we had said there was always, okay, 3 less than the number of sides. So here we go. 3 less than 4 is 1. That proves to be the case. Okay. 3 less than 5 is 2. Okay. 3 less than 6 is 3. And, okay, on our octagon, 3 less than 8 is 5. So generally speaking, we have, okay, if we have n sides, then we have a formula here, which is going to be the number of sides is going to be n minus 3, is for the number of diagonals that we can draw from any one vertex, n minus 3, okay? So we're going to put that up there. And then we said the number of triangles formed. I believe we said there was 2 less triangles than the number of sides. 5 sides gave us 3 triangles, okay? 6 sides gave us 4. And 8 sides give us 6. So there we have it. We're going to say that the number of triangles is always 2 less than the number of sides, okay? So it's n minus 2. And then what's the total interior angle? Well, again, why did we do this? We developed it into the number of triangles, knowing that each triangle has 180 degrees. So then if we have, okay, n minus 2 triangles, each at 180 degrees, then we would have that the total interior angle would be that formula, n minus 2, okay, times 180, all right? And there is what we're trying to do, is develop, okay, how we can find the total interior angle for any polygon, okay? So if you need to, watch this again, and hopefully it proved helpful.